Okay, so in Chapter 16, in a sense, we're going to wrap up everything that we've done this semester. It's like the pinnacle of studying electricity and magnetism, and that is when you talk about electromagnetic waves, which are light. So some of the things that we'll do in this chapter is we're going to look at all the equations that govern the behavior that we've seen so far, the things that we've studied. Basically, we call that set of equations Maxwell's equations, and you'll see that they look very familiar, and they go back to early in the semester and when we were studying electrostatics. From those equations, Maxwell is actually predicted that these things called electromagnetic waves would occur, and that the thing about electromagnetic waves, which is a really long way to say light, but it does include things besides what we think of light, and we'll see that eventually, can travel through nothing. They don't need a medium, so that's a different type of light, a different type of wave, sorry. And they travel at the speed of light that we're familiar with. We're going to see that the speed of light comes out from the derivation of the expression for electromagnetic radiation. We're going to talk about if the waves are thought of as sinusoidal waves, and we're also going to talk about how light carries energy with them. We are not going to talk about standing waves. Sorry about that. One of the things I want to say before we really get into it is that a lot of the mathematics that helps us see how waves sort of drop out of Maxwell's equations is really math that's beyond what we expect at this point in your math career. And so you might look through the book, and as you're reading, it seems really weird. And in all truthfulness, there's a lot of hand waving in order to sort of get at these equations. And we're not going to go into a lot of detail about the mathematics. I think that what we'll be looking for in this chapter is just a really good conceptual understanding of light and how it is electromagnetic radiation, and some of the interesting facts about it. As we move past this chapter, we'll be looking at light in a somewhat different way, using some of the information in this chapter. But again, skipping the math is not really going to be a hindrance to you, but it's just something to be aware of. Now, one of the first things that we need to do before we look at Maxwell's equations is we have to actually sort of completely describe all the equations properly. And there's a little bit of a missing piece in Amperes' law that we haven't added yet. If you remember, Amperes' law was talking about how if you take an integral around a closed path of a magnetic field, that is equal to mu naught times the current that you have enclosed. So it turns out that Amperes' law, when we express it totally, there's a piece missing right now, and that's what we want to look at. So the good example that helps us see it is a charging capacitor. So here we have two parallel plates that are forming a capacitor. Of course, current comes into one of the plates, and that would be where the positive charge resides, and also leaves the opposite plate, which is where the negative charge resides. And we know as the capacitor charges, of course, there will be a potential difference across the plates. Therefore, there is also an electric field between the plates. But let's talk about why we're saying that there's a problem with this equation. When we think about integrating around a path, sort of inherently that path also is like the bounds for a surface. And in this picture over here on the left, they are actually showing two possible surfaces that are bound by the path, which is labeled with C. The two surfaces are basically just a circle, that's S1, but then the other surface is sort of a bulging surface that extends and kind of passes through and encloses that one charged plate, and so that's S2. Now the problem is that when you look at it, for surface 1, when you do the integral of the magnetic field around that path C, you do enclose the current that's coming up to the first positively charged plate. But if you go around the path for S2 and you're doing that integration around the path C, you don't actually enclose any current. And this is a problem. Another way we can look at this problem is from the point of view of continuity. In continuity, we could say, okay, there's current that comes into the positive plate, and then there's current that comes out of the negative plate. But what about the area between the plates? We don't have any traditional current between the two, and so it seems like that's kind of weird. That's like what we would call in physics a discontinuity. I go up to a point with current, all of a sudden it stops. It's not existent for a certain distance between the plates, and then it starts again. And so the idea is to propose that there's something called a displacement current between the plates. If we did that, and if we called that maybe I sub d, I know it's hard to see, then we would actually have continuity. And so this is what we're going to be looking at to correct Amperes' law. Okay, so we want to try to figure out how do we express the displacement current. Between the plates. So first of all, let's just remember some expressions for capacitors. If we call this a parallel plate capacitor, we know that there's two different ways we can write its capacitance, Q over V, or epsilon naught A over D. And so what we're going to want to do is, from these two expressions, I'm going to write an expression for V. V is going to be equal to Q times D, and remember this is D, the distance between the plates. Q times D over epsilon naught A. Now, the potential difference across the plates is E times D. And so if we wanted to find what we're looking at is the electric field could be expressed as Q over epsilon naught A. And if we want to look at the flux, because what is happening is there's a flux that's changing, so we multiply this times A. Okay, so this actually then is the electric flux. And I have to multiply this by A also, so I get Q over epsilon naught. Okay, so, all right, why am I doing this? Well, I said that I wanted to find some sort of current, and current is equal to dq dt. So if I take the time derivative of both sides, that is, if I took the derivative of the electric flux between the two plates, that would also be equal to 1 over epsilon naught times dq dt, which now, in a sense, I could call that dq dt, that I could call my displacement current. And so from that, my displacement current could be written as epsilon naught times the derivative of the electric flux with respect to time. And so what I would want to do is, when I look at Ampere's law, before we just had this current enclosed, but now I want to broaden this definition so that this would include both what I might call I sub c, which is sometimes referred to as the conduction current, because that's sort of the normal current that we're used to, but I'm also going to add to it my displacement current, which is the current that I said could be expressed this way. And that allows me to not have some sort of, discontinuity. If I included the displacement current in the expression, it wouldn't matter if I used surface 2 or surface 1 when I was doing my integral. I would still be enclosing some sort of current. And it also allows for me to not have a discontinuity when I look at coming up to the plates, going between the plates, and then coming away from the plate as well. I would always have a current the whole way through that path. And so in the end, what we do, how we modify Ampere's law, is that it'll be written as mu naught times I plus mu naught epsilon naught d phi e dt. In a sense, saying that another way to create a current is with a changing electric flux. But another important thing to notice is that, remember before we talked about how this current was creating this magnetic field. Now we also see that another way to create a magnetic field is through a changing electric flux, which would be a changing electric field. That's important, and we'll want to remember that fact. So we kind of get to our ending point with our expression for our displacement current. And now we can summarize everything that we've done into 4 basic equations that are said to describe all electric and magnetic phenomena, and these sets of equations are called Maxwell's equations. We see the top one was Gauss's law, which it seems like ages ago that we covered that. We also talked about Gauss's law for magnetism. You might have read about it. We didn't do a lot of it in class. We had Faraday's law, which we just covered very recently. And now we have our improved Ampere's law that includes the possibility of the displacement current. These are very important equations. If you actually say, well, what would happen if these equations were in empty space? What do we mean by that? We mean in an area where there wasn't any charges or there wasn't any current present. Those expressions would change somewhat, and here we see them on the right-hand side, what they look like. Notice that Gauss's law has been set equal to 0 because there's no charges. Notice also that our conduction current in Ampere's law is gone. But it's the bottom 2 expressions that are really important for us in this chapter, because basically what you're seeing is this equation is saying that a changing magnetic flux, which is probably caused by a changing magnetic field, can create an electric field. And then Ampere's law is saying that a changing electric flux or a changing electric field can cause a magnetic field. That's really important. So James Clerk Maxwell's really important. You notice we called that set of equations Maxwell's equations. But he really, what his big contribution was for us today is that he saw in these equations that if he manipulated them, they were basically implying the existence of waves that could travel through space without a medium that consisted of electric and magnetic fields. And this was called electromagnetic radiation. And this is also what we know as light. It includes visible light, and that's what we usually mean when we say light. But we'll also see that it includes other types of electromagnetic radiation, such as ultraviolet light, infrared, radio waves, microwaves, gamma rays, X-rays. All of these are electromagnetic radiation. Basically, if we think about those last two equations, and when we said that a changing electric field could create a magnetic field, and a changing magnetic field could create an electric field, and that is really the basis of how electromagnetic radiation is being created. And that's also why it can sort of propagate through space without a medium, is because it sort of keeps making itself from the previous step. It's sort of like this endless loop that happens, and we'll look at a picture in a minute. Basically, we can see that like in power lines, which are carrying alternating current, they are actually accelerating charges back and forth, and this is going to generate electromagnetic waves. And so that's, coming back to these equations, that's kind of what we were getting at. I think I already really described, in a sense, what we were talking about here. So let's look at a picture that sort of helps us understand. So, for instance, if we have a piece of wire that's carrying an alternating current, you saw that alternating current when we talked about generators in the previous chapter. So this is what the current looks like over time. That's what an alternating current looks like. So it is changing. And remember that you learned that if you have a piece of current wire, it will create a magnetic field around it. There you see the blue loop. And so we see that there's that magnetic field going in a circle around the wire, but because of the fact that that wire changes with time, the magnetic field that it's creating that circles it will also change with time. Then we look at, through Faraday's law, we can look at a loop. The red loop here is, an electric field that's being created from the changing magnetic field. That's through Faraday's law. Then we go back, and then the changing electric field creates a changing magnetic field. And so you see that these things keep coming back and forth and back and forth. And as we move away from the wire, as this keeps happening, we're also talking about the propagation of this disturbance of electric and magnetic fields, and that's the way that the wave is moving. And we'll find out eventually that it's moving with the speed of light. And that's essentially what Maxwell's equations predicted. And again, here are the equations we can sort of think about of how they are creating each other. In the first picture, we see, the changing electric field created by the alternating current is going to create the magnetic field, but that magnetic field is going to vary. And so then we go up to here, and that changing magnetic field is going to create a changing electric field, and it just keeps going on and on and on. This is another picture from your book that's also showing it, sort of thinking from the point of view of a vibrating charge, because as the current's traveling, the charges are actually vibrating back and forth. And then again, you're seeing that the light is traveling outwards, consisting of these electric and magnetic fields, and traveling at the speed of light. In the next slides, we'll look a little bit about some of the details of this, of the math involved, but not a lot, just kind of talking about what kind of waves govern the behavior and so forth. We don't really need to know how to derive them. We just kind of want to know that they exist.